Hey guys, this is AF, and in this video we are going to be discussing numbers. When I talk about numbers, the first thing that comes to mind are the different types of numbers, and while there are many, we are only going to be concerned with a select few. The biggest set of numbers that we are going to be dealing with are called real numbers. These are numbers which, when squared, give us a value that is greater than or equal to 0. And this right here is just rule written in set notation. Now it's completely fine if you're not familiar with set notation at this point, since this is a separate chapter that we're going to be dealing with in future videos. If we consider the examples of real numbers, we find out that numbers such as 1, 2, 3, 4, and so on, as well as their negative opposites and 0, are all examples of real numbers. Similarly, both positive and negative fractions, as well as almost all constants, including pi and the Euler's constant, are examples of real numbers. Within real numbers, there is a smaller group of numbers which are called rational numbers. These are numbers which can be expressed in the form of a fraction a divided by b, where b cannot equal 0 because if that is the case, then the entire expression is going to be undefined. Examples of rational numbers include numbers such as 1, 2, 3, 4, and so on, as well as their negative opposites and 0, as all of these numbers can be expressed as a fraction with 1 in the denominator and themselves in the numerator. Obviously, all fractions, whether negative or positive, are also examples of rational numbers. Within rational numbers, there is an even smaller group of numbers which are called the integers. Integers consist of numbers 1, 2, 3, 4, and so on, as well as their negative counterparts -1, -2, -3, and so on, and 0. Positive non-zero integers are given another name, that is natural numbers. So natural numbers are 1, 2, 3, 4, 5, 6, and so on. Most of the syllabus of O-level math revolves around integers. One group of numbers within real numbers that we discussed are the rational numbers. There is another group of numbers which are called the irrational numbers. These are numbers which cannot be expressed in the form of a fraction a divided by b. Examples of irrational numbers include some constants, for example pi and the Euler's constant, and it also includes the nth root of any integer x, where x cannot be expressed as another integer y raised to the power n. Now, at first, this rule sounds a little complex, but once you get the gist of it, it's actually quite simple and will help you solve any question regarding irrational numbers where you will be asked to quote an example of them. Moving on, let's have a look at a few numbers and try to describe them. If we have a number such as 3.1, our first instinct should be to square it and see whether or not it is a real number. Now, when squaring the number, that is multiplying it with itself, we need not to get an accurate value, but an approximation would do. In this case, since we know that 3.1 is just slightly larger than 3, we know that the square of 3.1 is going to be slightly larger than the square of 3, which is equal to 9. Therefore, we can say that 3.1 squared is greater than 9 and obviously greater than 0 and therefore a real number. Now, to check whether it is a rational or an irrational number, try to express the number in terms of a fraction. In this case, we can say that 3.1 is equal to 31 divided by 10, or even 62 divided by 20, or any other variation of this fraction would do. Now we know that it is a real rational number. We can see by looking at the number that it is not an integer because integers are basically non-decimal numbers. What if the number is a little peculiar? For example, 2 pi divided by 3. Even in this case, we're going to go down the same path. As I mentioned earlier, we need not to get an accurate value of the square of this number, but rather an approximation. In this case, we're going to be approximating the value of pi to be equal to 3. If pi equals 3, then this number is going to become equal to 2, which when squared is equal to 4. Therefore, we can say that when this number is squared, its value is approximately equal to 4. However, since we know that pi is slightly greater than 3, this number, when squared, is going to be greater than 4. At the same time, we are aware of the fact that pi is an irrational number. Therefore, all its multiples are going to be irrational as well, and we can describe this number as a real irrational number. Now let's try to describe the square root of minus 5. When we square this number, the answer we get is minus 5, which is less than 0, and therefore we can say that the square root of minus 5 is a non-real number. You need not to classify it further because non-real numbers are not a part of the syllabus. Though these types of numbers have never been tested in the actual examinations, I included an example to give you an idea of what a non-real number looks like. Moving on, let's try to describe the fourth root of 25. First, we're going to square it, and the answer we get is the square root of 25, which is equal to 5. And since 5 is greater than 0, we know that the fourth root of 25 is a real number. If you recall the rule that we discussed when I was talking about irrational numbers, I said that the nth root of any integer x will always be irrational provided that x cannot be expressed as another integer y raised to the power n. So now I need to see if 25 can be expressed as another integer raised to the power 4. If that is possible, then this number is a rational number. If that is not possible, then I can say that it is an irrational number. And since 25 cannot be expressed as another integer raised to the power 4, I can say that it is a real irrational number. Moving on, let's discuss a few more different types of integers. Now, these types of integers that we're going to be discussing now are very simple, and I'm sure that you're already familiar with them. One set of numbers is called prime numbers. These are numbers which only have two factors. They do not have more than two factors. They do not have less than two factors. Examples of prime numbers include numbers such as 2, 3, 5, 7, 11, 13, 17, 19, and so on. Take 17 for example. It only has two factors, 1 and itself. Another important fact about prime numbers is that they are always positive. Another type of numbers are called square numbers. These are numbers which can be expressed in the form x squared, where x is an integer. Like prime numbers, square numbers are always positive as well. This is because if the initial integer x is negative, when it will be multiplied with itself, the product is going to be positive. If the initial integer x is positive, when it is going to be multiplied with itself, the product is obviously also going to be positive. Examples of square numbers include the number 4, 9, 16, 25, 36, 49, 64, and so on. 36, for example, can be expressed as the square of 6. 49 is equal to 7 square. Another type of numbers are called cube numbers. These are numbers which can be expressed in the form x cubed, which is basically x multiplied by x multiplied by x. Cube numbers are both positive and negative. Examples of cube numbers include 8, which can be expressed as 2 cubed, 27, which can be expressed as 3 cubed, 64, which can be expressed as 4 cubed, 125, which can be expressed as 5 cubed, and even minus 8, minus 27, minus 64, and minus 125. Now let's have a look at a few different past paper questions which are going to give you a very good idea of how these concepts are likely to be tested on the actual examination. The question says, state an irrational number between 1 and 2. Now, there are multiple approaches to questions such as this, but one approach that I found very easy was to express the given information in the question in the form of an inequality, which would look something like this. X is greater than 1 but less than 2. Now square the entire inequality, which gives us the new inequality x squared is greater than 1 but less than 4. Take a square root of the entire inequality. Now at this point, it might seem quite like a futile step to first square the entire inequality and then take a square root of it. But if you look closely, you have the answer right in front of your eyes. The square root of any number between 1 and 4 is your answer. It could be the square root of 2 or it could be the square root of 3. Similarly, you could also answer in terms of pi and say that it is equal to pi divided by 2. Let's have a look at another question. Write down two prime numbers whose sum is 15. Now, the way I would approach this question would be to go through the prime numbers one by one and see which number would I need to add to it to make it 15. For example, if I have the prime number 5, I will have to add 10 to it to make it 15. But 10 I know is not a prime number, and therefore this is not going to be the answer to this question. So if you go in order, the first prime number you will have is 2. Now, to make 2 15, I'll have to add 13 to it. 2 and 13 are both prime numbers, and therefore I have the answer by thinking just about the first prime number. Let's have a look at this question. Write down an irrational number between 3 and 4. Now, you could use the inequality approach that I discussed above, but a far more easier way to answer this question would be to just say that the answer is equal to pi, because the value of pi is 3.14 to two decimal places, so it lies between 3 and 4. Moving on, let's have a look at this question. The first part states, find an integer r such that r is greater than 5 and 5r minus 1 is a square number. One approach to this question would be to plug in different values of r greater than 5, which would be 6, 7, 8, and so on, and see whether or not 5r minus 1 is a square number. But a far smarter approach would be to realize that multiples of 5 always end at either 5 or 0. Let's go over the multiplication table of 5. It has 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and so on. All of the multiples of 5 end at either 5 or 0, and 5r is obviously going to be a multiple of 5. Therefore, 5r minus 1 will always end at either 4 or 9. So now you only need to look for square numbers which either end at 4 or 9. Two numbers that I can think of right now are 49 and 64. If 5r minus 1 is equal to 49, then 5r is equal to 50, and r is equal to 50 divided by 5, which is equal to 10. If 5r minus 1 is 64, then 5r is 65 and r is going to be 13. Both of these answers are correct, and there may even be more answers to this question. The second part states, find the value of s which makes 8s plus 2 a prime number. One thing you could have done to solve this question would be to express it in factor form, which would be 2 multiplied by the expression 4s plus 1. If the value of 4s plus 1 is equal to 1, then when it's going to be multiplied with 2, the answer will be 2, which is a prime number. So the only thing you need to do is to give a value of s for which 4s plus 1 is equal to 1, and that value of s is equal to 0. The next part states, find an irrational number between 7 and 8. For this question, we're going to use the inequality approach that we discussed above. So first, we're going to express the given information in the form of an inequality. We're going to square the inequality, simplify it, take a square root of this inequality, and finally, we have the answer right in front of us. The square root of any number between 49 and 64 is the answer to this question. So we could say that x equals square root of 50. Let's have a look at another question. This question will be the last one that we're going to be discussing. A list of numbers has been provided. It includes 0.2, 2, square root 2, 1 divided by 3, 0.83, 8, and 81. The question says, from the numbers listed above, write down a prime number. I know that prime numbers are a group within integers, therefore all prime numbers are integers. So I can filter out all the non-integer numbers and just have a look at the integer numbers. In the given list, there are only three integers, 2, 8, and 81. 81, I know, has more than two factors. So does 8. However, 2 only has two factors, 1 and itself. Therefore, the answer to this question would be 2. To write down a cube number from this list, again I'm going to be looking just at the integers, which are 2, 8 and 81. 2 is a prime number and therefore cannot be a cube number. So I'm just left with two options, 8 or 81. 81 cannot be expressed in the form x cubed, where x is an integer, whereas 8 can be expressed in the form 2 cubed, where 2 is an integer, and therefore the answer to this question would be 8. Finally, we need to write down an irrational number. For this part, I can filter out all the integer numbers. So I am left with 0.2, which I know can be expressed as 2 divided by 10, 1 divided by 3, which is a fraction itself and therefore a rational number, and 0.83, which can also be expressed as 83 divided by 100. So I am left with the square root of 2. Now, to check whether or not it is a rational or an irrational number, I'm going to see if the rule that we discussed when we were talking about irrational numbers is applicable here. So if 2 can be expressed as another integer raised to the power 2, then it is a rational number. If that is not possible, then it is an irrational number. And since I know that 2 cannot be expressed as another integer raised to the power 2, square root 2 is going to be an irrational number. I hope that you found this video helpful. Thank you and goodbye.